Today we are going to start a new topic that is called liquid extraction. This is a thermodynamic process where there is an equilibrium of the solute in two different phases. So liquid extraction has many advantages and it is widely used in bioprocess downstream technology. It is a mass transfer operation. So you have a liquid feed, it could be a fermentation broth or a reaction broth which contains the solute or metabolite or the protein which you would like to recover. You use a solvent, the solvent is immiscible solvent or very sparingly miscible, and this solvent will extract preferentially the solute of your interest. You cannot say that only one solute will get extracted, because after the end of the fermentation broth you may have a large number of metabolites. So you may have some of the unwanted metabolites also getting extracted, but that is possible. So typically in a liquid extraction you have a stage where you make your feed come in contact with the solvent. The solvent could be a low density liquid or it could be a high density liquid. So once the contacting is done and you allow the two layers to separate out, that means if you want the two layers to separate out there has to be some difference in the density. If the density difference is very small, then the separation is not very efficient and it may take a very long time to separate out. So in that situation you may resort to a centrifugation type of operation. So the two layers get separated out and the solvent layer may be in the bottom if it is very heavy or maybe in the top if it is light, and this solvent carries the solute of your interest. So here you have the extract which will have the solute rich solvent layer, and you have the raffinate which would be now either devoid of the solute or will have less amount of solute when compared to the feed. Now these two streams, that is the extract and the raffinate, will be in equilibrium with each other. The solute partitions between these two phases. So the key word here is partition. So there is something called a partition coefficient which determines how much of solute from the feed goes into the solvent layer. If the partition coefficient is very large, then your solute will be predominantly found in the solvent layer. So you select a solvent which will have a very high partition coefficient, so that you will have more of the solute into the solvent layer. Sometimes you may have to do it in many stages, instead of just one single stage you may have to do it in 2, 3 multiple stages. So here in a batch process, if you consider you mix your solvent with the feed thoroughly, agitate it with a stirrer and then stop the stirring so that the two layers get separated out, and then you take the solvent layer which contains more of your solid, and you can now take the original feed and perform another extraction process. This is how we do it in our lab. So liquid extraction is very simple. All you need is a separating funnel and you can do it in your lab very efficiently. It does not require high temperature or pressure, it is done in ambient conditions. So it is very ideal for solutes which are very temperature sensitive. It is very ideal for proteins because proteins will never get denatured. So it is very widely used technique, except that the solvent should not denature your protein of interest. Sometimes the solvent may take away the water present in the enzymes, thereby denaturing your enzyme or protein. So that is the only point you need to keep in mind. So it is ideally used for low molecular weight lipophilic products like antibiotics, organic acids from fermentation broth, or if I can use a aqueous two phase extraction system for even high molecular weight substances, antibodies, proteins, enzymes. So this technique is widely used for a large number of separation and purification downstream processes. It is a thermodynamic process, as I said, because there is an equilibrium between the streams that are leaving the stage. Advantages of liquid extraction: you can very selectively extract a particular metabolite or protein. So by selecting your solvent or aqueous phase, selectivity can be tremendously improved. It is done in ambient conditions, so stability or instability problems is not a issue, and we can use it at wide range of scales. As I said, we can practice these in your lab, or you can take it to thousands of liters scale in an industrial setup as well. So as long as you are able to have a solvent which has a very high partition coefficient, as long as you can recover the solvent and reuse, then this is the best method for even for large scale operations, and of course we do it regularly in our lab as well actually. But there are problems also you need to consider when you are resorting to liquid extraction. There could be solids present in your fermentation broth. This can give rise to phase complexities and it can influence the extraction process. That means the separation will not be a clean two phase separation. There could be a small layer where there could be some of the solids precipitated out may be present, so there some of your product of interest may get lost. So instead of just having two clear layers, the solvent and the raffinate layer, you may also have a solid layer in between. If there are surface active species, then your mass transfer rates gets disturbed. That means mass transfer of the solute from the fermentation broth or feed rich layer into the solvent layer. Number 3, if there are surface active species present, then these will affect your phase separations. There could be adsorption taking place which may reduce the efficiency of separation. There could be chemical instabilities as well. So the desired product when getting extracted may lose its activity because of changes in pH, changes in compositional conditions and so on actually. Then the rheological properties also are getting disturbed. If you take a fermentation broth and if it contains cell mass, dead cell debris and so on, it will be highly viscous, and we need to now mix your solvent with such a highly viscous fermentation broth. So the rheological properties will have a bearing on the extraction process. So you need to keep those points also in your mind actually. So there are many parameters which affect your liquid extraction process: the type of solvent you select, how efficient it is, what is the partition coefficient of your solute in the solvent. So all these issues needs to be considered. So when you select your solvent, we need to consider all these points. We will talk about it in the subsequent slides on solvent selection. Operating conditions: what should be my temperature, what should be my pH and so on. These are the operating conditions. If I am using a continuous extraction, what will be the flow rate of the solvent, what will be the flow rate of the feed. If I am using an agitator, what should be the agitation speed, and then if I am going to allow the two layers to separate, how long should I allow them to separate. So all these points have to be considered, and that is called the operating conditions. Mode of operation is the third point. That means, should I do it in batch mode or should I do it in continuous mode? What is batch mode? You are allowing the solvent to mix with your solute, and then you agitated it well, and then stop the agitation, allow them to separate, then separate these two layers, again you introduce a fresh batch of your broth. That is called a batch mode. In a continuous mode, you are continuously sending in your feed, or you are continuously sending in your solvent, and then you are continuously drawing out the raffinate and the extract. That is called the continuous mode. We will look at some designs how where the liquid extractors are operated in continuous mode. Of course, the modes have advantages and disadvantages. Continuous mode you will get continuously constant concentration of solute in your solvent, whereas in a batch mode it is going to be a batch operation. So it is manpower intensive, it is a time consuming. So each batch product quality may be varying. So that is the disadvantage of the batch mode, but the batch mode can be operated at different scales, small scale, large scale, there is no problem, batch mode works very well, whereas continuous mode is ideal for very large scale operations. Extractor type, what type of extractor should I use? Should I have agitated extractors, should I have non-agitated extractors? I am going to show you many designs of extractors in the subsequent slides. So which type of extractors do I select? The next one is design criteria. What type of design criteria I select? Do I use mass balance, do I use steady state mass balance relationship, or do I use unsteady state mass balance relationships? Do I assume the extraction efficiency or the partition coefficient value to change from stage to stage? So all these criteria needs to be considered when you select a design methodology. So all these are the parameters you need to keep in mind when you are designing a liquid extraction system. So the principle of extraction, as originally I mentioned, is a thermodynamic process, and it works based on the partition or distribution coefficient. So the solute gets distributed in two different phases. So you may have a organic solvent, so the solute will have more solubility in the organic solvent, so it moves into the organic phase. So if the distribution coefficient is very large, then you will have a very efficient separation. If the distribution coefficient or partition coefficient is not so large, you may have several stages of extraction, you may have a train of extractors, and you will be, and each stage you will be extracting little of the solute. So overall you will be extracting the entire amount of solute of your interest. So the partition coefficient can be defined like this. K is the ratio of the solute concentration in the organic phase divided by the concentration of the solute in the raffinate phase. So generally concentration in the this solvent phase will be very large, so K will be much greater than 1. The higher the value of K, your extraction process is very efficient. The assumption here is it is independent of the solute concentration for a given solvent pair. That means if I have a particular solvent which I decide and a broth, K should be constant, it should not depend on the concentration, whether I do the extraction for a recovery of 1 millimole concentration of solute, or if I do the extraction for 1 micromole, K should be constant, it should not change. So that is the assumption here. So it is basically based on the thermodynamics, that means it is basically depending on the chemical potential or partial molar free energy. So the term that comes into the picture is the mu is the chemical potential. So you are adding your feed and you are adding your solvent, mixing it thoroughly, and then you are separating two different streams from the stage. So the two streams that are leaving the extractor are supposed to be in equilibrium, that means they attain equilibrium. So when they attain equilibrium, the chemical potential of the solute in these two phases will be equal. So that means mu H is equal to mu L. L is your light phase or the solvent phase, H is the heavy phase or the broth, fermentation broth phase. So the chemical potentials have to be equal. So main assumption here is the two streams that are leaving the extractor attain the equilibrium. That is an ideal condition, but generally sometimes we do not give enough time for the solute to partition effectively and reach an equilibrium. If the viscosities are very large, then the movement of the solute molecules from the heavy phase to the light phase takes a longer time, but I might not wait for such a long time. So they actually do not reach a equilibrium. But for design purposes or calculation purposes, we can assume that the chemical potentials of the streams leaving the extractor reach a equilibrium, that means they are equal. Another important point we assume is we generally for notational purposes we call the feed as the density denser or heavier phase and the solvent as the lighter phase, but it does not matter, sometimes solvents can be very heavy like your chloroform, but generally we assume for these sort of explanation purposes. So in a thermodynamic situation the chemical potentials are equal, that means the system has reached an equilibrium. So the chemical potential mu H can be written as mu naught H plus RT ln CH, that is the concentration of the solute in the heavy phase. This is equal to again mu naught L plus RT ln CL, that is the concentration of the solute in the solvent phase or the lighter phase. Okay. Now mu naught is called the chemical potential under standard reference state. As you know, in thermodynamics we always make our calculations starting from a standard reference, so that is why we call it mu naught, and R is the usual gas constant and T is the temperature. So we can rearrange this equation and we can get a relationship for ln K. Ln K will be equal to mu naught H minus mu naught L divided by RT, correct, and as you know K is nothing but Cl by Ch as I defined in the previous slide. So logarithm of the partition coefficient depends on the chemical potentials of the heavy and the chemical potential of the light at standard condition, and the temperature will come in the denominator. Okay. So K if I take, then you will have e power minus, just like an Arrhenius type of relationship you are going to get. So at equilibrium delta G is equal to 0 for a dilute conditions and ideal conditions. So K will be equal to E minus delta G 0 divided by RT. Okay. So K depends on temperature, just like an Arrhenius equation for rate of reaction, where there also we have a exponential raised to the power with a temperature term coming into that actually. Okay. If you remember the Arrhenius equation for reaction, K also looks exactly similar to that, correct. Now of course systems deviate from ideal conditions, no system is an ideal, because in a real situation you are going to extract a solute from a fermentation broth, so you are going to have many species, you are going to have solids present, you are going to have a highly viscous broth, you are going to have a biomass present, and then the extraction process you do not leave it for a very long time, so that the solute in both the phases come to equilibrium. So it is a non-ideal situation, and on top of that you are also going to have dissolution of one phase into another. For example, if I take a alcohol to extract something, a solute from a aqueous medium, alcohol may be soluble in the aqueous medium. Solute saturation in a phase, because a solute, any solute will have certain saturation solubility. So at that particular concentration condition it may have a non-linear type of behavior. Reaction of solute with the solvent, sometimes some solutes will start reacting with the solvent, then you cannot just assume there is a partition alone is taking place, there could be a reaction also taking place. Alteration of pH and other operating conditions during the extraction process, of course the pH is going to change, sometimes temperature may change, because when you take a cold solvent and use it to extract a solute from a hot fermentation broth. So these operating conditions also will affect my extraction process, so you will not have this type of a thermodynamic equilibrium taking place actually. So you need to consider that in reality there is a non-ideality which is taking place, and the streams leaving the extractor is not in equilibrium. Now the Gibbs phase rule says that P plus D is equal to N plus 2, where P is the number of phases, N is the number of components, D is the number of degrees of freedom. Okay. So what do we have? We have two phases, we have the feed phase and we have the solvent phase, 2 phases. Now component wise you have one component, that is your solute is getting partitioned either in the solvent phase or it is present in your feed or fermentation broth. So if you substitute that, you find that the degrees of freedom d is equal to 1. So you have only 1 degree of freedom. So if the concentration of the solute in the solvent phase is known, then automatically the concentration in the fermentation broth or feed is fixed. So there is no extra degree of freedom, there is only 1 degree of freedom for this type of liquid extraction. So you see the thermodynamics plays a very important role in this process, and the phase rule determines the number of degrees of freedom that are present for this extraction process. So if once you fix the concentration in the solvent phase, automatically the concentration in the feed phase is fixed, or if you know the partition coefficient, automatically both the concentrations are fixed. That means if you know the partition coefficient, the concentration of the solute leaving the stage in the solvent phase and in the raffinate are fixed, there are no more extra degrees of freedom after that. Okay. So it is the thermodynamics always works under very dilute condition, it will not work at a very concentrated condition, and at equilibrium both the phases have the dissolved solid, and the amount of volume of the solvent H is in large excess compared to that of the L. That means you always use a very small amount of solvent to extract your solvate, whereas your feed may have a very large quantity. So the concentration chemical potential of the solute in the heavier solvent may be taken as fixed and constant, and it does not change very much with small variation in the solute mole fraction or concentration. Another important point is the chemical potential of solute in the lighter phase, that means mu L increases with increasing solute concentration. Okay. So it will keep on increasing and it will finally reach a saturation, but mu L cannot keep on increasing ad infinitum, because there is a limitation on the solubility of the solute, and beyond a certain value no more solute can dissolve into your solvent phase. Okay. So what will happen is you will have the chemical potential of the solute in the heavies, that is given by this, okay, and then a chemical potential mu L keeps on increasing actually until it has to saturate out, because the solubility of the solute in the solvent is fixed, and that determines the amount of solute that moves into your solvent phase. Okay. So there are many other points which needs to be considered when you are performing a liquid extraction. Higher the partition coefficient, greater will be the extraction efficiency. Here very large number means extraction will be very good. Large density difference between the extractant and the raffinate, you can achieve good separation using gravity alone. That means after the mixing you can allow them to settle from each other, so there could be a separation, you will get a very nice phase separation because of gravity. But if the density difference is smaller, then you may have to resort to some sort of a centrifugal separation. High viscosity of the solvent affects the phase separation, because as I said your fermentation broth will be highly viscous because of cell debris, biomass and other proteinaceous material which have come out of your broken cell. So the movement of the solute from the heavies into the light is very slow. Next point, there should not be a miscibility of the solvent into the heavies and vice versa, otherwise you are losing some of the solvent into the heavies which is lost actually. So the idea is you have to minimize the solvent loss. Now you should be able to after the extraction remove the solvent from the solute which has been used for extracting actually, because your solvent has to be purified and again recycled for further extraction because the cost plays a very important role in your downstream of, and the solvent recoverability is a main issue in the overall operating cost. The solvent should be easily available, we do not want to use many exotic solvents because then it may be very expensive and it will add to the extraction cost. If you have very low interfacial tension between the phases, then dispersion of the phases is good and it also improves the mass transfer. But then if you have the low interfacial tension, then the phase separation becomes difficult, the phase separation takes much longer time. So the separation will be taking a very long time, so hence your overall throughput also becomes very low. The physicochemical properties of the solvent like the boiling point, density, interfacial tension, viscosity, corrosiveness of the solvent, flammability of the solvent, stability under operating condition, compatibility with the product, availability should be satisfactory. So you have a large number of requirements while selecting a solvent. For example, it should not be corrosive to the material of construction of your extractor, it should not be a flammable, that means you should not use solvents which are highly flammable or have very low boiling point, because a lot of solvent will vaporize during your handling and you will be losing solvent as a vapor, and also you will be having possible explosion hazard or flammable hazard if the solvent goes into vapor phase. The solvent should not deactivate your metabolite or protein of interest, so it should be compatible with the product. So we need to select a solvent which satisfies all these conditions. So selecting solvent plays a very important role and it depends on the type of product which you are trying to recover. Number one, it depends on the pH conditions of your fermentation broth, and it depends on whether it is aqueous or a non-aqueous situation. For example, free base is more soluble in non-polar organic solvents than in polar organic solvents, okay, like water or aqueous base. So you need to keep that in mind. Quaternary ammonium salts of amines formed during reactions are more soluble in polar or aqueous media than non-polar organic solvents, because it is a salt and it is a quaternary ammonium salt, so it will be stable in polar or aqueous solvent. If the aqueous solvent is basic, amine compounds may be in the free base form. Free acids may be more soluble in an organic solvent than in water or acid. Salts formed by the reaction with base are more soluble in aqueous media than in organic solvents. Acidic aqueous medium will be in the free acid form and so will partition into organic phases. So all these points tell us the pH determines what type of solvent to use. If there are salts present, you have to select a suitable solvent at an appropriate pH so that your compound is stable and it does not lose stability during the extraction process. Now if you have acetic acid in water, if you want to recover that, N-butanol, ethyl acetate, MABK, toluene and hexane can be used to extract acetic acid. N-butanol will be having the highest and hexane will be having the lowest extraction ability, because N-butanol has having the highest and hexane having the lowest miscibility with water, okay. So when you have a group of solvents, each solvent looks a feasible opportunity for extracting your solute. Within that group you can select based on the miscibilities, based on the extraction ability as well. Now as I said, if you take a fermentation broth, it may have several metabolites, and most of the time when you are using a solvent to recover one metabolite, more than one may also get extracted during the process. So there is something called the selectivity of extraction. So if you have two metabolites A and B and you are using a solvent to extract A, and B also may get extracted, so the ratio of Ka divided by Kb, that means the ratio of partition coefficient for the solute A divided by the partition coefficient for solute B, that tells you the selectivity of extraction. That means how much more of A I will be able to extract than the amount of B. If Ka and Kb are almost equal, then my beta will be almost equal to 1. That means when I am using this solvent for extraction, I will be extracting both A and B. Then later on I may have to separate again A and B. If I am interested only in A, then B is a wasteful product which is also getting extracted. So I need to select a solvent which will have more selectivity towards A than towards B. That means Ka should be much larger than Kb, so that although I will extract some B during the extraction, my predominantly the solvent will contain only A. So it is not only that the partition coefficient has to be very large, but the ratio of partition coefficient for A and B, that is Ka by Kb, also should be large, so that my selectivity towards A is also large. So that is a big problem, especially when we have several metabolites present from a fermentation broth, because I will be having several partition coefficients. I may have Ka, Kb, Kc, Kd and so on. So many of these metabolites may be getting extracted during the process, and I may have to look at Ka by Kb or Ka by Kc, Ka by Kd, Ka by Ke and so on, and look at the selectivity terms and decide on a suitable solvent. So that is again a very challenging task. And similarly, if I have many proteins and my solvent is picking up all these proteins, then I need to select a solvent which will be more preferential towards A than towards protein B or protein C or protein D, or I may have to do this extraction and later on go to a chromatography type of situation to just pick out the protein of your interest. We are going to talk about chromatography later on, and you may resort to different types of chromatography at that point. So initially you will go for a solvent extraction, and in the process you may extract many proteins, and then you go to a typical chromatography which will extract or which will just pick up only the protein A from a mixtures of protein. So your downstream may have a extraction and then you may have a chromatography. If it is metabolites, then you will have an extraction. Then if the metabolites are stable at different temperature conditions, I may go to distillation, where you may separate out A, B, C from one another. Okay. So for a protein you may have extraction followed by chromatography or chromatographies. For a metabolite small molecule which is stable at different temperature conditions, I may go to extraction followed by distillation, because distillation is always cheap. As long as your metabolite is stable at all conditions, you may resort to distillation rather than going to chromatography. So the selectivity term, the separation factor beta, is also very important when you decide on the solvent. There are many equipments used for extraction. In your lab, no problem, you will have something called a separating funnel. You take your broth, you add some solvent, mix them, and then leave it for separating. So a separating funnel will be slowly tapering down with a bottom discharge. So after mixing them thoroughly, you will allow them to separate out into two layers, and then the bottom layer you remove it by opening a cork which is located at the bottom of your separating funnel. So all the labs we always have a separating funnel which is tapering downwards, but in large scale operation you may have to resort to many different types of mixing separating systems because of many problems which we said, because of non-ideality, because of the viscosity conditions, and you want to do this entire operation very fast. So the mass transfer limitations, the movement of the solute from the heavy to light needs to be speeded up. So you need to create turbulence between the two different liquids, so that the solute moves very fast from the heavies into the lights. So it is not only the thermodynamics, you are also wanting to improve or speed up the kinetics. Okay. Two types of equipments predominantly used are equipments which have mechanical agitation, equipments which do not have an agitation, mechanical agitation, but there is a counter current intimate mixing between the two phases which creates the turbulence and mass transfer movements. I will show you some pictures of many equipments which are used in industrial scale liquid extraction processes. A simple batch type of situation which is called a mixer settler batch extractor. You have a mixer, you have a settler. In the mixer what do? You add your feed, you add your solvent, close down, mix it thoroughly, create good intimate contact, and afterwards what do? You discharge the whole thing in a settler, you allow them to phase separate into the heavy phase and the light phase. Your solute may be here if the solvent is light, solute may be here predominantly if the solvent is heavy. So then you leave it for several hours until the phases separate, and then you discharge the bottom, you discharge the top, and then if you have the fermentation broth, again you may carry out one more mixer settler, again you can put it here, you can take another fresh solvent here, again allow it to come in contact with each other, again you can do a mixer settler. So you can have a series of mixer settlers, a train of mixer settlers possible. So this is called a batch operation, and the mixer settlers are very easy to construct. So you need just two tanks, one tank will be agitating, other tank will be non-agitating, where you allow the phases to separate into two distinct layers. But there is always, as I said, non-ideality comes into picture. So the interface between the two layers may have some solids which has precipitated out, it may have a combination of both these phases, you may have the little bit miscible solvent into the heavies. So the middle portion will not be very sharp, there could be another layer which needs to be disposed of. This is a batch operation. You can have several types of continuous operations. You can have something called the system counter current type of situation, where the solvent flows in one direction, your feed flows in another direction. If your solvent is heavy, then you add the solvent from the bottom, top, and it comes down, it picks up your solute, it extracts your solute, so it comes out as a extract, and your feed travels upward and comes out as a raffinate. The feed will have less of your solvent. For light solvents, you introduce the solvent from the bottom, it rises up, your feed is heavy, relatively heavy, then the solvent, so the feed travels down. So the extract comes at the top. So this is two different continuous column extractors, one for the heavy solvent and one for the light solvent. Now the internals of this column can be very different. You can have different types of internals, like in distillation column. I will show you pictures of few of the possible internals, because you want the solvent and the feed to come in good contact, you need to generate turbulence so that there is a mass transfer of the solute from the heavies goes into the lights. So you need to create a very high mass transfer rate. there are a large number of continuous extractors as you can see from this picture. This is called a static bubble column. So you have one liquid which is static, it creates a large tall height, the other liquid is introduced in the form of a bubbles. So there is a mass transfer and the interface between the bubble and the bulk of the liquid where the solute moves from one phase to the another phase. The mass transfer in such situations are bit low. The next design is called the sieve plate column. So you have many plates which perforations. So when the liquids travel, one going from the top to bottom, other going from bottom to top, because of these sieve plates there is going to be some turbulence created and there is a mixing taking place in each portion of this sieve plate. So this is called a sieve plate design. The third design is agitated column. So you have a tall column and you have a agitator with many blades. So the agitator rotates, so at each level there is a mixing taking place between the two phases and there is a intimate contact and mass transfer takes place. The fourth type is called the spray column. That means one of the liquid is sprayed. This liquid can be your solvent or it could be the heavies, it is sprayed and again it creates fine bubbles. When you create a fine bubble, the mass transfer area is very large, as you know mass transfer area plays a very important role in the kinetics of extraction. So finer the bubble, more is the mass transfer area, so higher is the rate of extraction. Fourth design is called a packed column design. Here you have a column with inert packing. So as the liquids travel, because they move through the packing, there is intimate mixing. The packing acts as a location for the two liquids to come in contact with each other. It provides a surface area for the two liquids to come in contact and the transfer of the solute from the heavies to the light takes place. The fourth design is called the rotating disc. So you have a very fast disc rotating and one liquid is introduced from here, other liquid is introduced from this side. So this liquid, because of the centrifugal action, is thrown out, and this liquid which is introduced here, when this liquid is thrown out at very large G values, they come in contact, a large mass transfer is created. So there is a mixing taking place and the mass transfer of the solute takes place actually. So the force with which the liquid that is introduced here hits the other liquid creates a large turbulence and creates the necessary mass transfer for the transfer of the solute from the heavies to the light. When compared to things like bubble columns and spray columns, the interaction that is created in rotating disc is much higher because of the centrifugal force of one of the liquids. So there is a much better intimate contact and the rate of mass transfer is also much higher. So these are called centrifugal separators. So centrifugal separators are used if the density difference between the two liquids are not very high. Then there are other designs. The first one is called the Cooney column, the second is called the Schiebel column, the third one is called the Carr column. So in Cooney column you have agitators as well as you have sieve plates. So each region between two sieve plates acts as a single stage extractor and there is a good mixing inside this stage because of this agitator blade. So when you have many sieve plates and many blades, you are creating automatically several stages where in each stage there is a mixing of the liquid and the heavies. So you can move the solvent from the bottom up or from top up depending upon the density of the solvent with respect to your fermentation broth. The next design, this is called a Sheibel column. So instead of sieve plates you are partitioning the column into several stages. Again the principle here is you are creating several stages next to each other. So the two liquids come in intimate contact in each of the stage separately, whereas in your Cooney column you are using sieve plates, here you are using certain partition baffles to create this stage effect. The third type is called the Carr column, where the agitator moves up and down. So when the agitator moves up and down, the blades also move up and down, so they create a turbulence and brings in a intimate contact between these two liquids. So you see a large number of designs using mechanical or using a non-mechanical type of setup, where you are trying to bring in a good degree of contact between the two liquids, so that you can improve the rate of mass transfer of the solute from the heavy to the light, that means solvent. So from the feed to the solvent layer, because the rate of mass transfer determines how long you can do this extraction process, and if you want to improve the throughput or you want to increase the throughput, the rate of mass transfer has to be very high. Okay. Each of these designs have advantages, disadvantages. This table gives you some idea of the advantages, disadvantages of each one of them. So one important thing is number of stages present in each one of the design, the flow rate, that means the throughput, what is the residence time, what type of physical properties of the fluid that can be used, and what is the floor area occupied. Floor area occupied is also very important, because if you have the extractor spread all over the floor, then you are using up too much of the area, plant area, whereas if the extractor is vertically placed, then you are occupying less floor area, which is advantageous, because more floor area, more space you will require, more space you need to spend money on buying that space. If you take mixer settler, it does not have many stages, so it is very low, L means low. Flow rate can be high, I can have very large mixer settlers, so I can process a large amount of liquid. Residence time is also very high, because I will do a mixing for a long time and then I will do a settling for a long time. Physical properties, I can use different types of fluids, different types of fermentation broth to carry out this particular operation. Floor area occupied will be very high, because I will require some space for the mixer, I will require some space for the settler. So you see many disadvantages. Centrifugal separator, it does not have many stages, flow rate also has to be low, residence time is low, so that is good. Floor area occupied is much less when compared to a mixer settler. Whereas if you go to a column extractor, that is vertical column, static column, agitated column, we saw a large number of columns. If you look at static column, it has some number of stages, flow rate is medium, residence time is medium, the floor occupied is very low. When you have agitated column, it has many stages, like I talked about some of these Carr column and so on, or sieve plate column, Sheibel column, all these columns, they have many stages possible, and each stage can act as a single ideal thermodynamically ideal unit, where there is an intimate contact between your solvent and the feed. Flow rate can be medium, residence time can be medium, floor area occupied is very minimal. So the columns design occupy less space, and if you look at agitated columns, then it also has a large number of stages. That is why industrial scale operations are always done in agitated columns rather than mixer settler. Mixer settlers are very cheap, I just require 2 tanks, but it has got a lot of disadvantages when compared to say an agitated column, where the design needs to be properly organized, but it has many advantages when compared to the mixer settler. Centrifugal also has a few advantages, but the number of stages are minimal. So I may have to have 2 or 3 different types of centrifuges if I want to perform a centrifugal type of separation. Static columns are good, it does not require any mechanical agitation, that means you do not require motors for agitating your column, but the number of stages are much less when compared to agitated columns. So that is the disadvantages of static column, but the main advantage is I do not require a mechanical agitator, that means I am saving on not only the purchase of a motor and agitator, but I am also saving on electricity if I want to operate a motor, which I need to utilize if I have a agitated column. So each of these design has advantages, disadvantages, and as I said, generally nowadays industries prefer agitated columns because of several advantages when compared to several other types of design. Okay, we will stop with this.